Hey, this is Math 105 section 4.2. In this section we're talking about the natural exponential function using the lowercase letter e. Okay, so we can use any positive number as a base, okay, for an exponential function. Okay, so we're going to study the base e, which is we use for a lot of calculus applications. Okay, so first we'll talk about where e comes from. Okay, so the number e is a constant, and it's an irrational number, sort of like pi. You know, the decimals just keep going, and we can't write it as a fraction of integers. So we take 1 plus 1 over n to the nth power. So we start with that, and then we make n become large. Okay. And when we do that, what happens is, so we take 1 plus 1 over n to the nth power. Okay. So, for example, for n equals 10, we have 1 plus 1/10, which is 1.1 to the 10th power. When n equals 100, we have 1.01, 1 plus 1/100th to the 100th power. Okay. And then when n equals 1,000, we have 1.001, 1 plus 1/1000th to the 1000th power. So what we're doing is we're taking, numbers getting closer and closer to 1, 1 plus a very small decimal to a very high power, okay? Now that doesn't approach 1. It actually approaches this number, 2.71828, which is our e, okay? So that's where e comes from. So that's what the 1 plus 1 over n to the nth power is. Like 1 plus 1/10th to the 10th power, 1 plus 1/100th to the 100th power, 1 plus 1/1000th to the 1000th power, etc. So for certain values of n, here's what we get using this. So for 1, it's just 2, right? 1 plus 1 over 1 is 2 to the 1th power is 1, right? For 5, it's 2.488832. For 10, it's 2.59374, etc. So for 100, it's 2.70481. Okay. For 1,000, 2.71692. For 10,000, you see as we get higher values of n, we're getting closer and closer to this value, which is 2.71828, which is e to the 5 decimal places. So we can estimate e is 2.71828. So that's a constant. That e is always this number, and that's an approximation because we have other digits. But as we get higher and higher for n, we're going to see that those first 5 digits are 2.71828. Okay, so we can say that it appears that correct to 5 decimal places, e is about approximately equal to 2.71828. Okay, and then to 20 decimal places, e is approximately this number. Okay, we're not going to go that far out. Okay, e is an irrational number. Okay, so we can't write its exact value in decimal form. The decimals keep going, right? So we would just have this ... here. Okay, saying they keep going, and there's no pattern to them, just like pi. Okay. Okay, when we talk about the natural exponential function, okay, we're using e as the base. Okay, it might seem that a base such as 10 is easier to work with. Okay, but in certain applications, in fact, most calculus applications, number e is the best possible base. Okay, so when we use it for compound interest, it makes much more sense. So we actually use the natural exponential function more than any other one, okay, because it has certain qualities, especially in calculus, that make it very useful, okay, and make other bases not quite so useful. Okay, so the natural exponential function is just f of x equals e to the x, where e is that 2.71828 with base e. Okay, and sometimes we just call it the exponential function because it's kind of the most common one that we use. Okay. Okay, we know that since e is 2.71828, it's between 2 and 3, right? So the graph of the natural exponential of the exponential function lies between the graphs of 2 to the x and 3 to the x. Okay, so we can see that the green is 2 to the x, that aqua is 3 to the x, and then the red is e to the x. See, it's between those two, but it's closer to 3 to the x because 2.71828 is closer to 3 than it is to 2. So there's our exponential function, our natural exponential function, e to the x, just closer to 3 to the x. Okay, and if you have a scientific calculator, you'll see an e there. That's what this refers to. Okay. So if you see your e to the x key on your calculator, you can put in the exponent, then just press in e to the x and it'll give that. So if we're looking at like estimating e to the third power using a calculator, we would just type in 3 and then hit that key. And then we can see it's about 20.08554. Okay. 2e to the minus 0.53, we would start with the minus 0.53 and then hit the e to the x and then go times 2. And that would give us about 1.17221. Okay. E to the 4.8, we would put 4.8 in first and then put e to the x key, and it will give us about 121.51042. So, you know, we're not going to do things by hand with e where we're multiplying e out a number of times, but we can use a calculator to estimate, you know. Okay, we often use the exponential function in something like an infectious disease model. Okay, so here's our example. We have an infectious disease that begins to spread in a small city of population 10,000. After t days, so t is time in days, the number of people who have succumbed to the virus would be v of t, would be the people who have succumbed to the virus, is modeled by this function. So v of t is like the population that's in fact succumbed to the virus, is 10,000 divided by 5 plus 1,245 times e to the minus 0.97 t. Okay. How many infected people are there initially at time t equals 0? And find the number of people infected after 1 day, 2 days, and 5 days. So we're going to put in our days for t here. Now let's talk about this function for a minute. And I'm going to kind of go over to the side here and think of what e to the minus t looks like. Okay. If this is e to the t, right, that goes like this. Okay. And let's ignore the t part for a second. Okay. Well, we'll ignore where t is negative. So let's see, this is e to the t. Okay. E to the minus t is, and let's say this is our t, is like our x. Okay. So e to the minus t is going to reflect across the y. Okay. So it's going to go down. Okay. So what we're focused on here, so this is e to the minus t is the red, right? Okay. And that's what we have here, that e to the minus, it's almost like e to the minus t, minus 0.97 t. But we're kind of focused on this part. Okay. See, we're looking at t as a positive quantity, right? We're not looking at negative t. We're just looking at t in days from, you know, start at t equals 0 was the initial time, and then we're going forward in time. So what we're doing is we're taking our exponential function and flipping it across the y. So now this part, we're looking at kind of the tail end here going this way. So it's going down. So this thing is slowly decreasing. Okay. This e to the minus 0.97 t is slowly going down, okay? And it starts at 1. Well, it starts at 12:45, sorry. See, it's going to start here. And so that the e function is, this thing is slowly going down from 1, because when t is 0, this is 1, right? So we have 12:45. So then this kind of goes down from 1. I'll say slowly going down from 1. From 1, okay? So this number is going to get smaller. You know, it's going to be 1245 times 1, and then 1245 times 0.9, and 1245 times 0.8. So what's happening is our denominator is starting at 1250, okay, because this is 1, right? And then the denominator is getting smaller because this e to the minus 0.97 t is shrinking, okay? So as it shrinks, it makes this 1245 get smaller, so our denominator gets smaller, which means ultimately this thing is getting bigger. Okay, there's a lot going on there. But see, because it's in the denominator and this thing is getting smaller, we're making our denominator smaller, starting at 1245 plus 5, because this is a 1 to start. And then this thing goes down, so now this thing gets smaller, which means our denominator gets smaller, which means the v of t gets bigger. So that's how it grows. And that's considered an exponential model, but it's using the exponential function kind of in a, you know, it's sort of embedded in this fraction, right? So just to get an idea of what's going on there, because it's not obvious. Okay, so as I said, when t is 0, e to the minus 0.97 t, and I put the previous page up there so we can see the function again. Remember, it's 5 plus 1245 times e to the minus 0.97 t. I know that's a little bit hard to see. But when t is 0, we have e to the 0 there, so that becomes a 1. So then we have 10,000 divided by 5 plus 1245, which is 10,000 divided by 1250. So we start with 8 infected that have the disease. Okay. Now we look after 1 day. When t is 1, this becomes 21. See how fast that grows? and then at day 2 it becomes 54. Okay, we plug in t as 2 here in this model. Okay, and then at day 5 it's 678. So this is actually growing really rapidly. Okay, because this denominator is getting smaller and smaller. Okay, because this e to the minus 0.97t is decreasing from 1. It's becoming a small fraction. So we're adding just a small bit to the 5 in the denominator. Okay, and as we go, this number infected gets bigger and bigger. Okay, but then after a certain point, now this is v of t is the y, and then t is days. So let me write that in there just so we know. Okay, so this is t, and this is v of t. So this is number infected. Okay, or number that are succumbed to the virus. Okay, so you can see, and we see it's going up really rapidly. Okay, but after it gets to about 2,000 people, okay, about 1/5 of the population has succumbed to the virus. It starts to level off. So as t gets we go more and more days, this thing starts to level off a little bit. Okay. And it's not going to be quite as many infected. It's sort of like it reaches sort of a state of stability. I don't want to say stability, but kind of a state where we have a certain number of people infected, and it's not really increasing or decreasing. It's kind of staying about the same, and that happens when, in this case, when about 1/5 of the population is succumbed to the virus. Okay, so it does grow quickly, but it doesn't mean it just keeps growing. So this kind of a model is good for modeling, using the exponential function is good for modeling diseases, infectious diseases, because that is kind of what happens with a lot of infectious diseases, is that they start to spread, and then there's a certain period where they start to grow rapidly, and then at a certain point, at a certain percentage of the population, maybe in this case it's about 1/5 of the population for this model, that it kind of starts to level off. Okay, so we can see that the number of infected people first rises slowly, then rises quickly between day 3 and day 8, and then levels off when about 2,000 people are infected. Okay, we also use our exponential function for continuously compounded interest. We didn't talk about this yet, but remember we talked about compounding interest annually or semi-annually or monthly or quarterly or weekly or daily. Continuously means you're constantly calculating interest. Okay. And that, remember we said that, n was number of times per year. If we're doing quarterly, n was 4. If we're doing daily, n was 365. Well, now for continuous compounding interest, we're kind of saying n is like infinity. Like we're constantly contacting interest. We'll say it's not exactly infinity, but it's approaching infinity, right? So, so how do we do that? Okay, this requires some explanation. So let's look at this. Okay, this is our formula for compounding interest, right? Where n is the number of times per year, right? And r is our interest rate, and t is number of years, right? This is what we saw from section 4.1. Okay, now we're going to do a little something funky here. We're going to take this 1 plus r over n, and we're going to make it n over r to the rt. Okay, now it's still n times t, but we put an r. What we did was we divided by r, and then we multiplied by r again. Okay, so it's kind of like a wash, but we're doing this for a reason. Okay, now we're going to say, now that we have this part inside the brackets, okay, we're going to let m equal n over r. Okay, so m is n over r. Okay, which means that our n over r here becomes m, right? And this is r over n, so that's 1 over m. Okay. Now, if m is n over r, okay, remember interest rate is finite, right? It's like if it's 5%, it's 0.05. And we make n go to infinity, then m will go to infinity too, because m is n over r, right? So as n gets really large, so does m, okay? So think about what happens to this thing when n gets really big. When n gets really big, m gets really big. And this is just what E is, right? The quantity 1 plus 1 over m to the m approaches the number E as m gets really big, okay? So what happens is this thing just becomes p e to the rt. Okay? In other words, this thing right here is e when m gets really big. Okay? So that's all we have for compound interest is a equals p e to the rt. Okay? Very simple. Once you understand this, how we did this, right? We made n really large, but we had to do a little funky thing here with algebra to get that e there. Okay, so this is our continuously compound interest. That means we're like constantly compounding interest. Is just a amount in the account equals principal times e to the r times t. We don't have to worry about n, right? So it's very easy. Okay, and this expression gives the amount when the interest is compounded at every interest. In other words, at every instant. In other words, you're constantly compounding interest. Okay. Not something you're physically doing, but if you do that, it's actually going to level off to that e. Okay, for continuously compounded interest, by using this formula, a of t is p e to the rt. You can think PERT is an easy way to remember that, p e r t. Okay. A is the amount after t years, p is a principal. That's how much we invested. R is our interest rate, is a decimal, okay, and t is the number of years. We don't need an n, right? Okay, so let's look at an example of that. Find the amount after 3 years if we invest $1,000 at an interest rate of 12% per year, compounded continuously. Okay, so our p is 1,000. That's how much we're investing. Okay, our r is 0.12, or 12% is a decimal. Remember to divide by 100, so you move your decimal place over 2. Okay, and t is 3. Okay. So we have A equals P e to the RT is our formula, right? So we have the amount after 3 years, okay, is A is P e to the R times T, or 1,000 e to the 0.12 times 3, which is 1,000 e to the 0.36, which is about $1,433.33. Okay, and when you're doing these interest calculations, anything involving dollars and cents, just round to 2 decimal places, because we don't round beyond the penny. So we're getting our final number. So just when you get your final answer, just round to 2 decimal places. So we have dollars and cents. Don't round to the dollars. Round to the hundreds place, which gives you cents as well. Okay, we'll tie this in with using compound interest like monthly and daily and weekly, etc., to see how this all fits together. But basically, if you were to do this calculation daily, you'd get almost the same number. Okay? Monthly would be pretty close. So this actually continuously doesn't really raise it that much more. Okay? After a while, it starts to level off. Sort of like not exactly like, but sort of like our infectious disease model that we looked at. It levels off. So if we were to do the same calculation for 3 years, daily or monthly, it would be pretty close to this 1433.33. Okay, I'll show that in class.